both videos, not the entire thing, number one. And number two, I haven't done epsilon delta proof since I tutored kids in college calculus, which would have been, I guess 2 years ago. It's probably the last time I tutored Calc 1 for college kids. And then 4 years ago. And then, anyway, it's been a little while. So, you were supposed to be solving for the epsilon delta proofs. Is that how they are?
Yeah.
What's an epsilon look like? Oh, it's a backwards E. No, but it's not an uppercase epsilon, it's a lowercase epsilon, isn't it? He was doing a sigma?
Yeah.
That's a 3.
Epsilon is the little swirly.
No.
Yeah, this is epsilon.
Yeah.
Epsilon and delta. Did I do it the wrong direction? Oh, I did it the right direction.
It just kind of looks like a sigma.
Oh, low ciento. Okay, I'll rewrite my epsilon. Now that we're back. Okay, epsilon delta proofs. And my delta's prettier too. We're doing the limit as x approaches 4 of what?
2x minus 5.
You could stare at it and be like, duh. And a college professor could be like, 0 points on your first test, a question worth 10 points. Because you didn't prove it. Bummer. But it's obvious. You won't care. Okay, so, what do you do?
Step 1 is the absolute value of x minus a.
But in this case, it'd be the absolute value of gain. Okay, what about the absolute value of x minus 4?
Good question.
Wait, you solved the example. Hold on, just walk me through
And then he just goes, alright, step 2, x minus L.
Okay, so you set that up. Aren't they steps, the game plan? So then f of x.
Minus L.
Which is 2x minus 5 is f of x, and then minus L is the limit, right? 3?
Yeah.
Okay, good. So then we simplify that, and we end up with? Factor out the 2? And I can pull the 2 out of the absolute value mathematically, right?
Yeah.
Okay.
Step 3.
Mhm.
2 delta equals epsilon over c, and c is 2.
Oh, you're reading how you did. I did.
That's step 3.
I don't have any excuse.
The absolute value.
X minus 4 is less than 8.
Delta is less than delta.
Okay.
Then consider the absolute value of f of x minus equals
2x. Absolute value.
the absolute value of 2x minus 5 minus 3.
Oh, so he actually showed the work.
It's the same thing.
Is it okay if I just go straight there?
Yeah.
Okay. Okay.
Plus
Delta
2 times epsilon over 2. And then
If you cancel it out.
I don't know what the answer is.
The triad.
And then you put
And
the
then
box
the box
of,
with
no,
the
no, the box
flower.
of flour, yeah.
There you go.
Wait, he did the 3 dots and he just boxed it?
And then
Yeah,
the
he
flower.
boxed
Just
it.
boxed.
Literally just said
Consider. Yeah.
Oh, so he didn't do this, he did the
He
flower
did
instead.
both.
He did both.
Like some people like doing this, but I like doing
I don't know, I just boxed
Okay. That's new.
So he just boxed the entire four.
And then made a flour.
Yeah, and then made a flower. So it's the dot, and then boxed it 4.
And he put the 3 dots after.
No,
Yeah.
he did 4.
No,
he
Ricky,
did
you
three
did it
dots.
right
He
now.
did
both.
He
Dots
did
down.
both.
He did the box.
No, he
No, he
did
did
dots
the
first,
box.
then the box.
I don't think it.
That-
Wait,
that's-
in the box.
Oh, it was.
Like that? That means QED in some mathematical proof. Sorry.
You put the 3 dots and then you box like all of the steps and then you
box
huge
the
flower.
entirety of 4 and the dots.
But it looks like
She's like, I can't turn.
No, it's funny the way you guys are explaining it. Hold on, get to the end, and he does all of that. We already did. I let you guys listen to it again. Oh, look at his color coding! I want to listen to his explanation for what he's doing here with the 3 dots.
Function is a minute is smaller than epsilon is, has, been, shown. Some people like to do that.
So
We're going to be over trying to do proof. Oh my gosh, you love.
Okay.
Oh my gosh.
Yeah. He really did just do a 3 dot. His 3 dots, he's trying to say therefore, but he's doing it in an incomplete way, which is a little bit weird and awkward. Because usually this is the beginning of a concluding statement. So it's kind of like, therefore, or, yeah, so. I was like, therefore what? I don't, therefore box with a flower. Maybe a better way of putting it is the limit as x approaches 4 of 2x minus 5 is. That'd probably be a better way of doing it. Therefore, like, what have you just proven? You've just proven that is true with an epsilon delta proof. And you guys did have a secondary video, and that had, what, 1 or 2 more examples? Just 1 more example. And so this is a weird way of proving as far as you guys, because I have taught calculus in very much a problem-solving, exploration, discovery sort of way, not in a, hey, we're giving justification for absolutely everything we're doing. I'm like, hey, it works, let's do it. And you're like, sweet, let's go. So I wanted just to give you a peek at how most calculus courses would have started by introducing the idea of proofs. And how a quick substitution is a shortcut to the real thing. So it is weird. Like, you're choosing a delta equals epsilon over 2. Like, why on earth are you doing this? Why are you doing all of this sort of stuff? And you're simplifying. And just imagine, like, what if this was an absolute value function? Or what if it was a radical function? Or a trig function? Like, how much more complicated would this have become? This one was super nice because you were able to end up matching it very quickly with pulling that 2 out and the x minus 4's match, and it was really easy to get the delta in. But as soon as you bring trig in, as soon as you bring, logarithmic functions or exponential functions, they get messy. What was that secondary example that you guys had? What was the second limit that you were solving? Okay, so it was a cubic function. Oh, I didn't mean to do that. Sorry, undo. I wanted to copy, not paste. Which made it a little bit harder. Like, getting a higher degree polynomial is going to be a little more complicated, but it's not near as bad, once again, as trig or exponential or logarithmic. And we could have spent an entire week or 2 on this alone. And then it would have never been on the AP, which is why I don't cover it. But I did want to give you a little bit of exposure. So what changed? It's a little bit harder, but not crazy tons. The limit as x approaches 2 of the cubic function. What do we got? Oh, that was it? Just x cubed? Oh, that was nice. I thought it was going to be a big old long polynomial. Okay, so step 1, what did you form? Absolute value of x minus c, right? Or x minus 2. Number 2, what did you do? F of x, which is x cubed, good, minus L, good. Step 3. What do you simplify it to be? Because he simplified this one. It was a quick factoring out of 2. It was easy. But why is this one harder? Because it's a difference of perfect cubes, but how many of you guys are used to factoring cubes, right? Now, could you technically remember SOAP, same, opposite, always positive? Yes. And that you have x minus 2, x squared, same, opposite, and then always positive. Is it 4x and 4? Is that what it is? 2x and 4. Oh, I switched it. We should sue. 2x and 4? Yeah. Same, opposite. Oh, I was just doing this one. the last line. There we go. You could have memorized that, but you could have also done something like, hey, what would make this 0 would be plugging in a 2, not a negative 2, but a positive 2. So then x minus 2, assuming that's going to be a factor, you could have done a little long division or a synthetic division with the x cubed minus 8. You could have had some fun with that, and you would have gotten x squared plus 2x plus 4. But either way, apologies. Okay, now what? Do you simplify any further? Okay. Do you see how he's trying to relate? Right? Or see how he's trying to relate? Okay, now step 3. One absolute value?
No, next line.
Oh, you're on step 4 now, yeah?
Continuing step 3.
Okay.
It's like absolute value of x minus 2 is less than 1.
Why is it less than 1?
He said for the sake of this, we're gonna choose 1. For the sake of it.
Because you're thinking of really tiny values in it. Because as you're approaching 2, right? So if you're approaching 2, it could be like 2.5, 2.1, 2.01, 2.001, and all of those differences would be less than 1. So he was getting like infinitesimally close. But Kevin, can you explain it a different way?
He just said for the sake of the question, we're gonna choose 1. That's all he
That's helpful. I think that was with this though, right?
Yeah.
Or did you use it for that also?
He like said he plugged it in, and then he's like, you can see it that it's increasing for like that.
Okay. What comes next? Oh, he hadn't solved it. I thought he solved it. Sorry. Because whenever you have an absolute value with inequalities, you have to sandwich it, because then it could have been before the absolute value between -1 and 1.
Less than x.
1 is less than
X. Less than 3.
Yeah, you saw me going to 3 early. I apologize. Now what?
But like this middle step, where you were like x squared plus 2x plus 4. Let x equal 1, and then you plug the 1 into that.
Then you just plug in 1 for
Use any notation? X equals. Oh, see, I don't like the way I organized it. That's okay. You guys see where he's getting those values from, right? 9 and 6 and 10, 19?
Yeah.
Okay.
Even though it's 7, 7 and 1.
So we figured out a range of his x's based on as x is approaching 2, that quantity is some decimal equivalent less than 1. And then he applied that to the polynomial to figure out what the polynomial must be between. Okay, now what?
Less than 19. And then C equals 19.
Step 4.
Or does step 3 you did delta equals.
Yeah, we haven't done step 3 yet, have we?
That was
Choose delta equals
I thought we did stuff.
1 I literally just put just read the point of the problem. And then he did comment on
I never wrote a 3.
Oh yeah, if absolute value.
So
Good.
Then absolute value f of x
times the absolute value of x cubed minus 8. I don't know.
Well, then he goes.
I think he does x cubed minus 8, doesn't he?
Yeah.
And then he does his x minus 2.
Yeah. And then underneath, like,
Mm-hmm.
19 absolute value.
of x is 2. And then plus the 19 delta. And then 19 times yeah.
And then dots.
And then triad thing.
I tried out and then the box made flowers.
As x approaches, is it 2 is 8? Is that what we're doing?
Yeah.
Yeah.
How do we do it? Do it like this way. There you go.
That's a wonderful flower.
Thanks, I appreciate it. So if you guys notice this proof, you're actually kind of building what you end up using to prove. So you're actually making it kind of fit the form of the epsilon delta proof, which is kind of weird. Like there are steps to where these were very similar as to what he was doing. The math just got a little bit more complicated because over here it matched up really quickly with the, hey, just factor out a 2, no big deal. And then you have the 2 and the x minus 4. And he was able to build the proof really quickly, whereas over here with that whole 7 and 19 and the absolute values in my smartboard doesn't like epsilon delta proofs. Look, it's frozen. Let it go. Let it go. Yeah, nothing. Wow. It really doesn't like it. Oh, guys, this is sad. Okay, now what's the good news about the AP?
We don't need to do this.
You don't need to do epsilon delta proofs. What's the bad news about higher maths? Higher maths as in pure math, there's going to be a lot of proving where you're not just able to say like, oh, hey, my teacher taught me this trick once and said it was right. You actually have to say why or how the concept came about, which is why they are really difficult. For instance, Mrs. Regan's oldest daughter, Danielle, is going to UCI to start her PhD program in math. I think she starts it technically in 2 weeks. She's moving in this coming Saturday, though. And she's doing like a brushing up of her undergrad maths. And you have to do things like, hey, why is a real number plus a real number still a real number? I mean, it's not near that simplified. It's a lot more complex. But there are a lot of proofs to pure maths. Just in case any of you guys are like, pure math, what's that? It's a lot of proving. It's a lot of proving, but also understanding why a lot of things in calculus that are tricks are actually true. So a lot of what you guys are seeing in Calculus 1 and in Calculus 2, it's kind of like, hey, this is how it works. Hey, this is how it works. Hey, this is how it works. It's kind of more applied math than it is pure math. Pure math would be much more a discovery of what are all the fundamentals between all of these or behind all of these number systems and all of these ideas. She was doing some video lectures this coming weekend, or this past weekend, on differentiability. And I was like, differentiability, sweet, differentiation, but a lot of the proofs behind differentiability. And she said one of the hardest lectures that she had done as far as getting ready for a PhD program had to do with continuity. It was very complicated as far as why a lot of the proofs were true. So anyway, everyone take a deep breath. Let it out. Thank Jesus as you let it out that you don't have to do epsilon delta proofs right now. But there is a lot of rationale and a lot of books literally that have been written as to why the maths that you use in calculus every day are solid, are true, are able to be used. Much deeper and much more complicated than what I teach in class. Okay. So, point was kind of proven that there's more to limits than what we do, but that doesn't mean that we can't still keep our short, sweet version as long as we are very careful along the way that we're not making incorrect statements. Because these people who are grading your AP exams know a lot of this math behind why these concepts are what they are, why these tricks work, and so if you make some sort of invalid statement, they can be like, oh, you have no clue what you're doing. Now, you don't have to know all this proving, all this behind the scenes sort of stuff, but you do need to make sure that your work is flawless because they will count or they will find your mistakes in your FRQs if you make it. Anyway, all that to say, we get to kind of go about the short, sweet version of limits, but first, did you guys realize as you were writing notes that our book does not actually start with limits? Our book starts with rates. What do we know about rates of change? Who's this guy?
That's the definition.
That's not the definition of the derivative unless we put the limit as delta t goes to 0. So what is he without the limit? The difference quotient. Yeah, the difference quotient talking about some arbitrary change in y's over change in x's, and specifically, if you look at this one, wouldn't it be change in, think parametric change in heights, right? With respect to change in time. So something is theoretically falling if it's change in heights over change in time. Theoretically, something has a height and it's changing, which I guess really in the graph I gave you, something is rising. Because what is the slope, or what is the instantaneous rate? Positive. So technically something is rising in these examples in this general illustration that I gave you, but down here it's going to be applied to falling. So this is over some sort of t interval, right? And t interval would be some sort of t is within, a to b, some initial time to some final time or ending time. Over some sort of t interval, time has passed and you have measured the height that it has fallen. Instantaneous rate of change. Now, John, this is what you were saying a second ago. He was like, limit of the definition, or sorry, definition of the derivative. We would have to go ahead and have that change in time go to 0, right? To get to that instant. To get to an instant, we need a change in time to get smaller and smaller and smaller. So what's going on down below when I have a rock falling at y equals 16t squared feet in the first t seconds, and I have solved the limit as h goes to 0 of 16t plus h squared minus 16 times 2 squared all over h. What has changed? Here's the general definition. Now it's been applied to a function that's been given to us, but what else has changed, guys? There's a constant, yeah. Isn't there a 2 in there instead of a t? Or a 2 in there instead of an x? So what does it represent? Do you remember how there's another form of this? Couldn't we also do d by dt, or the instantaneous rate, at some sort of t equals a? What would change in our definition of derivative? It'd be f of a. So when you see a constant, remember that's talking about a specific time minus f of a all over delta t. True. So who's this guy actually representing? Not f of a, but you're close. Oh, it's not even scrolling down. That's okay. I'll just leave it there. Remember last year in all your forever quizzes what I would take points off for? Or I would continually tell you don't forget to write? Not just the limit, but also what it equals. Now I did put d by dt such that, but what's another way of writing that, guys? F prime, or you could do y prime if you're thinking parametric, y prime versus x prime. Y prime of a. Maybe I'm asking you the why or the what it represents too early. We were technically supposed to solve first, so how will we solve this? We are so quiet today. Okay, hold on. We're not doing epsilon delta proofs. We're solving a limit problem. And a limit that looks suspiciously, or maybe not suspiciously at all, like a derivative.
It'd be like 16 times h squared plus 2h plus 4 minus 16 times 4.
So I think Kevin right now is foiling and then trying to distribute and trying to cancel things out to plug in h is 0. Eventually we can reduce. He's thinking 0 over 0, keep going. Introductory limits. Or we could just derive it. Exactly, because isn't it just y prime of a? So if I know that y is equal to 16t squared, every now and then we can cheat just a little bit because of the knowledge that we're coming into this class and this course with. So yes, we could FOIL and we could simplify and we could do the difference quotient. We could reduce out the h's and we could plug in h's approaching 0. Or we could take a derivative and say, hold on, who is dy dt? 32t. So we could say y prime of t. It's equal to 32t. So what's y prime of? What am I going to plug in? A, and who is A? Y is it 2? Right? Because wasn't 2 plus h plugged in instead of x plus h or instead of t plus h? And who's h taking the place of? Delta t's, right? So 1 prime of 2 would end up equaling 64. So what does that represent? How would you write it as a sentence if you were trying to be amazing and show off the AP text? Why you want to scroll down? Yeah, okay, let's put rate of change and rock falling together in the same sentence, right? So the rock is falling at, your turn. The rock is falling, what Laney said, at
Instantaneous rate of change of 64 feet.
You're missing one key detail that they would want to see. That's what I was looking for. What does it represent? How fast the rock is falling when t equals 2 seconds. They didn't actually say that in the words, they showed it in the map. So over here, one-sided versus two-sided, we can remember that if we see A with a little bit less, that's coming from the left. A with a little bit more, we're coming from the right. That's one-sided limits coming from one direction or the other, which is really only super tricky if we're dealing with functions whose domain is not all real numbers, or when we're dealing with piecewise functions where all rules are off and who knows what might happen depending on what's been given. But how do we fill in a two-sided limit? The limit exists if
Equal.
and can I put that mathematically so? Wait a minute, hold on. Ooh, this is the definition of continuous, right? The limit as x approaches a from below equals the limit as x approaches a from above equals f of a. I should write that, right? No. Why can't I write equals f of a? Yeah, for a limit to exist, the function does not have to exist because the limit is all about the approach, not the act. It's about the journey, not the destination, the approach, not the act. So I'm not finishing the definition of continuous because a function does not have to be continuous for a limit to exist. The approaches just need to agree from below and from above. Good. Okay, let's get past all that epsilon delta stuff. Beep, 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 beep. Let's get to an example. You guys gonna rock it? Ready, set, take it away, cool kids. Show me what you know. P.S. There's a very nice little piecewise function. Beep. It goes linear and constant and constant and linear and a little linear. Show me what you're talking about. Take your time. Take your time. Limit as X approaches 1 from below. Isn't the diner dude headed to a height of 0? From above, isn't the dude headed to the diner at 1? But when you compare the two, doesn't the limit not exist? If I'm going to 2, I'm in total agreement from either direction, and I'm going to 1, so therefore the limit does exist, and it is 1. However, f of 2 is awkwardly at 2. The question is, could you have done that with the piecewise and not with the graph? Hopefully. Now, kiddos, quick review for all the different strategies of finding limits. Is that algebraically, not graphically, but algebraically, try to plug it in, and typically, for very nice functions where the domain is all real numbers, yeah, plugging in is totally fine. However, are there functions where plugging in is not totally fine? Yep, 0 over 0 or number over 0. Do you see how I have both options? Because rational functions are functions where you have a numerator over denominator, a function on top over a function on bottom. If there's a constant on bottom, it's not a rational function. It has a fractional coefficient. But if you have a function over a function, if g of x equals 0, well, hold on. Something that we should probably talk about is for either one of these, f of c does not exist. For either one of these, the function does not exist. There is a discontinuity at c if you have over 0. The function does not exist, but 0 over 0 doesn't exist, number over 0 doesn't exist. But for the limit, we don't care about the at, we care about the approach. Which is why we cannot write the limit equals 0 over 0, because we have to keep going and see if the limit does equal something. We can't say the limit equals number over 0. That just means DNE. We have to keep going, but not keep going with factoring and conjugates and all those sorts of things. But keep going considering the signs of, okay, something infinite is going on because I have a vertical asymptote. So I have to check the sign. Remember, for the limit to exist, I have to have the limit from below agreeing with the limit from above. And the reason that that is most important here with vertical asymptotes is because you can either have them in agreement to positive infinity and agreement to negative infinity, or disagreeing with one going positive and one going negative, which means the limit would not exist. So make sure, especially with vertical asymptotes, hold, they cancel out, then you can plug in, it's nice. Vertical asymptotes, I have to consider from above and below the vertical asymptote to see if they are in agreement as far as the infinities. But you know the answer for each one-sided approach is an infinity. You just have to check the sign. So a quick reminder of check the sign. Your AB note should be somewhere close. You could go back and review how we check the sign. Thinking about plugging in a little bit below, thinking about plugging in a little bit above, and checking the sign. So that's like a quick, everything to do with limits. Right? So what else is there? Well, what about the funny ones? Yes, we try plugging in. Then yes, we try playing with it. Rational functions, we have discontinuities, etc., etc. But then don't we have transcendental functions? Especially trigonometric functions that can have some issues. Yes, if they have some issues, we try to simplify. Maybe making tangent, sine over cosine. Maybe making sine squared, 1 minus cosine squared. Yeah, we can use properties. But even that might kind of fall apart to some extent. I'm not going to make you do epsilon delta proofs as to why this is true. It would be a mess. I'm not going to make you use squeeze theorem yet to talk about why these are true. But we can say these are what they are based on the Forever card from last year, which I believe was Forever card 3? Or am I wrong? Is it Forever card 3? I'll have you guys check. No, 2 was basic graphs. 1 was like trig properties and unit circle. I think it was Forever card number 3 with the special limits. But here's a question. Did you guys have this one last year?
I think we did.
I think we did too. We just didn't use it a lot last year. We'll use it a bit this year, especially second semester with sequences and series. That'll be fun. So where does that bring us? Dun, 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 dun. Work on limits without the epsilon delta proof. And every time you do a limit, you can just plug in, or you can just factor, or you can just use both these towels, you little cheaters. lucky stars that we're not doing epsilon delta proofs in here. Bye, guys. Although some people believe those proofs are beautiful. I'm not judging or discriminating against them.
Stand up.